We are going to learn this new existence of a unique solution theorem. Now, why do we need a new theorem? Because our old theorem is only valid for first order differential equations. But this new theorem is valid for higher order linear differential equations subjected to initial conditions. Okay. Alright, so let's get started. Now I want to break down this theorem into three conditions, three facts that you must check. Okay, so what are those three conditions? So the theorem says let a sub n x, a sub n minus 1x and so on, these a's terms, and gx be continuous on an interval I. So what are those a terms? Remember I said our differential equation is linear. And remember we identify these a functions as coefficients of y and its all derivatives. So what the theorem says is make sure these coefficients are continuous on an interval I. Okay, and not only that, the isolated function gx, which is neither a coefficient of y or its derivatives, that function better be continuous on that interval. Okay, so continuity of g and the terms of a. Okay, that a term. So that's the first condition on an interval I. Alright, second condition is and let a sub n x not 0 for all x in this interval. So what does that mean? What is so special about a sub n x? What is n? N is the order. So a sub n x is the coefficient of the term with highest derivative of y. Right? So we call it the leading coefficient. So the coefficient of the highest derivative term should not be 0 for each and every x value in the interval. Okay, so that's the second condition. Okay, so the second condition is the leading coefficient is not 0 for all x value in the interval. Third condition, if x is equal to x naught is any point in this interval. So what is x naught? Now this is an initial value problem. So we have initial condition. So initial condition means all the conditions should start at same x value, right, which is x naught, and the theorem says that x naught better be inside that interval too. Okay, so x naught should be inside the interval. So that's the third condition. Alright, so let's discuss about these three conditions. Let's break it down. Let's try to understand it. First condition, you should have your coefficients and your right hand side function or the non-coefficient function should be continuous inside the interval. Okay. Second condition, leading coefficient should not be 0 inside that interval. That means should not be 0 for every x value. So two contrasting things, right? One should be continuous inside the interval, one should be non-zero for every x value in the interval. Okay, so remember that. Third condition is now a little bit different, where it says something should be happen inside the interval. So x naught, the initial starting x value, should be inside the interval. So don't mix up the second condition and the third condition. Second condition says make sure that the leading coefficient is not 0 for every x value in the interval. But the third condition says a point initial x naught should be inside the interval. Okay, so don't mix up what should be inside the interval and what should not be. Okay, so let's try to understand why we need this theorem. Okay, the first condition is these coefficients should be continuous inside the interval. Let's look at an example. Okay, let's construct an example. 1 over x y double prime minus 2y prime plus y is equal to 0 on an interval negative infinity to infinity. Now first condition, what are the coefficients? Coefficients is 1 over x, and there's a coefficient here negative 2, the other coefficient here is 1, and the right hand side isolated function is 0. So these three are constant, they are continuous everywhere. But 1 over x is not continuous when x is equal to 0. And x is equal to 0 is inside this interval, right? So you are not continuous at 0 and you are not continuous at that interval because 0 is a part of that interval. So we violated the first condition. How can we fix that if we want to fix it? I can start this with 2 to infinity. Okay? Right? So now we skipped 0. So now 1 over x is continuous inside the interval from 2 to infinity because 0 is not a part of that interval. Okay? So that's how I describe the first condition. And it makes sense. Think about that bad interval, negative infinity to infinity. One of your coefficients behave badly in the interval. Right? So that's a problem for your differential equation. So the first condition makes sense. Okay, let's look at the second condition. What second condition said is that make sure your leading coefficient, so let's create a leading coefficient x minus 1. So leading coefficient here is x minus 1 because it's the coefficient of the highest derivative, which is highest derivative is 2. So x minus 1 is the leading coefficient. Now let's pick up an interval. Here's my challenge for you, 0 to infinity. Now what is the second condition says? Leading coefficient should not be 0 for every x value in the interval. So x minus 1 is 0 when x is equal to 1. Is 1 inside that interval? Yes. So x minus 1 is 0 for one x value in that interval, right? At least for one x value. So that's a problem. And think about this. When x is equal to 1, x minus 1 is 0, so that you are multiplying by 0. Y double prime multiplying by 0. That's bad for the differential equation, right? Because that's your highest derivative. That's your order, right? Order is 2. So we want to avoid that, okay? So this is a violation of second condition. How can we fix that? Let's choose an interval goes from 3 to infinity because we skipped that one. Now x minus 1 never becomes 0 inside that interval, 3 to infinity, right? So this is a satisfaction of that second condition, okay? Alright, so we only do this for leading coefficient, okay? Alright, now the third condition is, let's say, let's change the differential equation to a simple one, x plus 7, something like that. Okay, third condition says your initial condition should be inside the interval. So your initial x point, not the initial condition. X point in the initial condition. So let's write some initial conditions here. Y 0 is 2, y prime 0 is 5. And let's pick up an interval, 3 to infinity. Now the third condition said your initial x point, which is what? Which is 0, right? Initial x point, and is it inside 3 to infinity? No. Now why do we have this condition? Think about this. You want to find the solution for this differential equation that lives inside this interval, and the solutions should start at 0, right? That is what initial condition says. If you're starting, even if your starting point is not inside where your solution should live, I mean, that's bad, right? Your solution starting point is not inside that interval. That's bad. This is a violation of third condition. But here's a satisfaction of third condition. Let's say the interval from negative 2 to infinity. Now 0 is included, right? Now the initial 0 means that's the initial starting x point, okay? Now it is inside the interval. Or even your initial conditions can be y1 to y15. Starting x point is 1 and 1 is inside this interval. Good. You satisfy the third condition. So that is the assessment of those three conditions, okay, and how we use the theorem. So let's learn more examples in the next video, but I want to say one more thing. This theorem only gives you a guarantee. What do you mean by a guarantee? So this theorem says if you satisfy those three conditions, you can find a unique solution inside that interval. What theorem says is I will guarantee you that you can find a unique solution in that interval I, inside that interval I. But I am not gonna guarantee about other intervals. The intervals that you didn't care or outside that interval, I am not gonna comment on that. That's what theorem says, okay? It does not mean that outside those intervals you cannot find solutions. No, it's just this theorem says, I don't know about that outside those intervals, but let me give you an interval that guarantee you to have a unique solution. Okay, so it is pretty, in that sense it's pretty much similar to the first theorem that we learned. Okay, all right, so I will see you with more examples in the next video. Okay, bye bye.